Pick up a cup. Go on, pick it up. Move it from one side of the table to the other. You just teleported it. Well, no, you moved it, but what is the difference? Seriously. What is the actual physical difference between moving something and teleporting something? Because if you sit down and think about this carefully, really carefully, the answer is going to ruin your whole afternoon. When you slide a cup across a table, the cup is the same cup, same atoms, same arrangement, same chips on the rim, same coffee stains on the inside. It traveled through every point between here and there. It was always somewhere. At no moment during the slide did the cup cease to exist. There was a continuous path, a smooth trajectory, and every atom in that cup followed every atom ahead of it in a nice orderly procession from point A to point B. Teleportation says, forget all of that. The cup vanishes from one spot and appears at another spot. No travel, no in between, no path through space. It just shows up. And people hear that and they think, well, that sounds like engineering. Give us 100 years, 1,000 years, and some very smart people in lab coats will figure out the machine. Like flight, like splitting the atom, like putting a man on the moon. Just another impossible thing waiting for a clever enough monkey to crack it. But I want to show you something today. I want to take this idea apart, one layer at a time, the way you dismantle a watch, and show you where each gear breaks. Because this is not an engineering problem, this is a physics problem. And physics problems come in two flavors. There are the hard ones, where the laws of nature say yes, but nature makes you work for it. And then there are the ones that are forbidden, where the laws of nature say no. Not yet, no. Teleporting a human being falls into the second category, and I can show you why, step by step, until there is nowhere left to hide. Let's start simple. Let's start with what seems like the easy version of this problem. Forget quantum mechanics. Forget everything you've ever heard about particles and waves and Schrödinger's cat. Let's just talk about stuff. Ordinary, everyday stuff. Matter. Atoms. The building blocks. Your body is made of atoms. Everybody knows that. But do you have any idea how many? Think of a number. Whatever you thought, it's too small. Your body contains about 7 billion atoms. Let me say that more carefully. Roughly 7 times 10 to the 27th power. That's a 7 with 27 zeros trailing behind it. If you started counting those atoms right now, 1 per second, ticking them off the way you'd count sheep, and you kept counting without stopping, without sleeping, without dying, you would need about 200 billion years. The universe has only existed for about 14 billion years. You'd need about 14 billion more universes, lined up end to end in time, just to finish counting. Here's another way to feel it. If each atom in your body were the size of a marble, and you line them all up in a row, that line would stretch from here past the nearest star, past the next one, past the entire Milky Way galaxy, and keep going for about 10 billion light years. That's a significant fraction of the diameter of the observable universe, made of marbles, representing the atoms in one person. That's you. You're walking around carrying that much complexity and you don't even feel it. These atoms are not all the same, obviously. About 65% of them are hydrogen, the tiniest atom. 1 proton, 1 electron, that's it. About 25% are oxygen, big, hungry, electron-grabbing oxygen. Then there's carbon, the backbone of organic chemistry, the atom that forms 4 bonds and makes life possible. Nitrogen, calcium, phosphorus, a smattering of iron in your blood, some zinc in your enzymes, traces of copper, iodine, cobalt, selenium. There are about 60 different elements in the human body, in proportions that are remarkably specific. You need exactly the right amount of iron. Too little, and your blood can't carry oxygen. Too much, and it poisons your liver. You need calcium in your bones, and potassium in your nerves, and sodium in your blood. The recipe matters. The recipe is what separates you from a puddle of goo with the same ingredients. And before we go further, let me mention something people always forget about: energy. Suppose you could by some miracle scan a body and transmit the blueprint. You arrive at the destination. Now you need raw materials. 7 billion atoms, precisely sorted. Where do you get them? You could scavenge them from the local environment, but oxygen from the air isn't the same as oxygen locked in a phospholipid. You need specific isotopes, specific ionization states, specific chemical contexts, and then you have to assemble them. Every chemical bond in your body represents stored energy. Your body contains something like 7 times 10 to the 18 joules of chemical energy in its bonds alone. And if you wanted to convert the mass of a human body entirely into energy and back, Einstein's equation tells you the number E equals mc squared. For 70 kilograms, that comes out to about 6.3 times 10 to the 18 joules. That is roughly the energy output of a large power plant running for 200 years, just to convert one person to energy, and you'd need to do it again to reconstitute them. The energy cost of teleportation, even if everything else worked, would dwarf the output of every power station on Earth. So step one of teleportation would be scan all of those atoms, identify each one. Is this atom carbon? Is that one oxygen? Is this one hydrogen? That's just a label, a tag. You'd need a few bits per atom to encode which of the 60 elements it is. 6 bits would give you 64 categories, which is enough. 6 bits times 7 times 10 to the 27th atoms comes out to roughly 4 times 10 to the 28th bits just for the species labels. Already staggering. Already more data than every computer and server and storage device on planet Earth combined by a factor of about 1 million. But fine, let's keep going. Maybe someday computers are big enough, because knowing what kind of atom each one is tells you almost nothing about a person. You could have 7 billion atoms of exactly the right types, toss them in a bucket, shake the bucket, and you would not have a person. You would have a warm, wet, disgusting soup. What makes you you is not the atoms themselves. It is their arrangement, their positions. The way this carbon is bonded to that oxygen, which is bonded to that nitrogen in precisely the right geometry to make an amino acid, which folds into a protein, which locks into a cell membrane, which forms a neuron, which connects to 10,000 other neurons in your brain. So you need to know where every atom is, in 3 dimensions. To what precision? Let's think about this. A typical chemical bond is about 1 to 2 angstroms long. 1 angstrom is 10 to the minus 10 meters. That's 1/10,000,000th of a meter. If you place an atom even 1 angstrom out of position, you could break a bond that was supposed to be there or form a bond that wasn't supposed to be there. A protein that folds into a helix might fold into a sheet instead. An enzyme that was supposed to catalyze a reaction goes dead. A neuron that was supposed to fire stays silent. And if enough of these errors pile up, the person you reconstruct is not the person you scanned. They might be a corpse, or something worse. So you need positional accuracy on the order of 1 angstrom, 1/10,000,000th of a meter. Your body is about 2 meters tall. To specify a position within a 2-meter volume to an accuracy of 10 to the minus 10 meters, you need about 10 decimal digits in each of 3 dimensions. Wait, let me be more careful. The ratio is 2 divided by 10 to the minus 10, which is 2 times 10 to the 10th. To encode that in binary, you need about 34 bits per coordinate, 3 coordinates per atom. That's about 100 bits per atom just for position. But that's not enough. Your atoms are not sitting still. Every single atom in your body is in motion. Thermal motion, vibration. The molecules of water in your cells are tumbling and spinning and crashing into each other at speeds of several hundred meters per second. Even the atoms locked into the solid matrix of your bones are oscillating around their equilibrium positions. To reconstruct you faithfully, I don't just need to know where each atom is, I need to know how fast it's going and in what direction. Velocity. 3 more components. 3 more sets of numbers. Another 100 bits or so per atom, so we're up to maybe 200 bits per atom, times 7 times 10 to the 27th atoms. The total classical information content of one human body comes to somewhere in the neighborhood of 10 to the 30th bits. Some physicists have estimated higher numbers, up to 10 to the 42nd, depending on what level of detail you include. But let me be generous. Let me use the smaller number. 10 to the 30th bits. That is a 1 followed by 30 zeros. Now, the total data storage capacity of every computer, every hard drive, every server, every phone, every thumb drive, every magnetic tape archive, every single digital device on planet Earth, all of it combined, is currently about 10 to the 22 bits, 1 zettabyte, maybe 2. Your body contains roughly 100 million times more information than all the storage capacity of human civilization. If you took every hard drive on Earth, wiped them clean, and dedicated them entirely to storing the blueprint of one person, you would have captured less than 100 millionth of the data you need. But let's suppose storage isn't a problem. Suppose you've got a magic hard drive the size of a planet. Could you at least transmit the data? The fastest data transmission we have, fiber optic cables, can carry about 10 to the 10th bits per second. 10 billion bits per second. That's fast. You can stream a movie in seconds at those speeds. So divide 10 to the 30th by 10 to the 10th. That gives you 10 to the 20th seconds. How long is 10 to the 20th seconds? It is about 3 trillion years. Now the universe is roughly 14 billion years old. 3 trillion is 3,000 billion. So you'd need to wait about 200 times the current age of the universe to transmit the blueprint of one person, just to send the file, not to build the person, not to gather the raw materials, not to power the assembly machine, just to transmit the data from point A to point B through the fastest channels we know. And you know what? I still haven't gotten to the hard part. Everything I just told you, all of it, that was the easy layer. That was the layer where physics is being polite, where the universe says, well, this is absurd, but at least the idea is coherent. At least you could in principle imagine a scheme. The idea that you could measure the position and velocity of every atom, write it all down, and transmit it. At least that idea sounds sensible, except it isn't sensible, and this is where the floor drops out from under you. There is a principle in physics discovered by Werner Heisenberg in 1927. It is called the uncertainty principle, and it says something very simple and very devastating. You cannot simultaneously know the exact position and the exact momentum of a particle. And this is not because your instruments aren't good enough, not because you need a finer microscope, a steadier hand, a colder lab. It is because the universe itself does not contain that information in a simultaneously accessible form. Position and momentum are what physicists call complementary variables. When one becomes sharp, the other blurs. Like trying to see both sides of a coin at the same moment. You cannot do it, not because your eyes are bad, because the coin only has one facing side at a time. Let me try to make this more concrete. Imagine you want to find out where an electron is. How would you do it? You'd have to look at it, right? And how do you look at something? You bounce light off it. A photon hits the electron, reflects back into your detector, and you say, there it is. But here's the catch. Light has momentum. A photon carries momentum. When it bounces off the electron, it gives the electron a kick. The electron recoils. And the more precisely you want to know the position, the shorter the wavelength of light you need, because you can't resolve details smaller than the wavelength. But shorter wavelength means higher energy. Higher energy means a bigger kick. By the time you've pinned down the position to 1 angstrom, you've slammed the electron with a photon so energetic that the electron goes flying in some completely unpredictable direction. You now know exactly where it was, but you have obliterated any information about where it was going. You might try being gentler. Use a long wavelength photon, low energy, barely a nudge. Now the electron barely moves. You've preserved its momentum beautifully, but the long wavelength means your position measurement is blurry. You know, the electron is somewhere in this region, but you can't tell where in the region. The position has become vague. You gain momentum information and lost position information. And Heisenberg proved mathematically that there's no trick, no clever arrangement of mirrors and lenses, no sequence of measurements that can beat this trade-off. It is fundamental. Heisenberg wrote this down as a mathematical inequality. The uncertainty in a particle's position multiplied by the uncertainty in its momentum must always be at least as large as Planck's constant divided by 4 pi. Planck's constant is an incredibly small number. 6.62, 6 times 10 to the minus 34 joule seconds. Very small. But it is not zero. And the fact that it is not zero means there is a hard floor on how much you can know about a particle. No technology, no genius, no billion-dollar instrument can push below that floor. You could have all the money in the world, all the time in the world, the most brilliant engineers who ever lived, and you would still run into this wall. Because it is not a wall of engineering. It is a wall of mathematics, of logic, of the deep structure of quantum theory. So the scan I described earlier, where you measure every atom's position to the precision of an angstrom and simultaneously measure its velocity to comparable precision, that scan is not just impractical, it is impossible. Fundamentally, physically, mathematically impossible. The information I said you needed, all 10 to the 30th bits of it, the universe will not give it to you. You can pin down the position and lose the velocity, or pin down the velocity and lose the position, but you cannot have both. Not for one atom, not for any atom, and certainly not for 7 billion billion of them. And there's something even worse hiding inside this principle. To measure the position of an atom precisely, you have to interact with it. You have to bounce something off it, a photon of light, say. And to get a very precise position measurement, you need a very short wavelength photon. Short wavelength means high energy. A high-energy photon smacking into an atom gives it a massive kick. It sends the atom flying. You measured where it was, but in doing so you destroyed its velocity, its bonds, its relationship with its neighbors. The molecule it was part of may have shattered. Try this on the next atom and the same thing happens. And the next, and the next. Every atom screams, I mean that almost literally. If you tried to scan the atoms in a living person with the precision needed for teleportation, each measurement would be a tiny act of violence. A photon hits an atom, the atom recoils, the molecule it's part of twists and breaks, the protein unravels, the cell ruptures. By the time you've scanned a cubic micrometer of tissue, that tissue doesn't exist anymore. Not as living tissue, not as organized matter, as debris. The act of scanning at the precision teleportation requires is the act of demolition. It's like trying to understand a sandcastle by throwing rocks at it and studying the trajectories of the fragments. By the time you've mapped the whole thing, the castle is powder. Alright, so maybe you're thinking, forget the brute force scan, there's another way, there's quantum teleportation, the real thing, the thing physicists actually do in their laboratories. And I want to tell you about it, because it is real and it is wonderful, and it makes the problem worse. In 1993, Charles Bennett and 5 collaborators published one of the most elegant papers in the history of physics. They showed that you could transfer the complete quantum state of one particle to another particle at a distant location without ever knowing what that state was, and without the state traveling through the space between them. They called it quantum teleportation, and the name stuck. Here is roughly how it works. You start by creating a pair of entangled particles. Now, entanglement is one of those words that gets thrown around a lot without people understanding what it actually means, so let me take a moment. When 2 particles are entangled, their quantum states are correlated in a way that has no analogy in everyday life. It's often compared to a pair of magic coins, where if you flip one and get heads, the other always comes up tails, no matter how far apart they are. That image is useful, but misleading. Because with real coins, you'd just say, well, one was heads and one was tails from the beginning. There's no mystery, and you'd be right for coins. But for quantum particles, that explanation doesn't work. Bell's theorem, proven by John Bell in 1964, shows that the correlations between entangled particles are stronger than any pre-existing agreement could explain. The particles aren't carrying hidden notes that say I'll be heads. They genuinely do not have definite states until they're measured, and yet they're correlated. Einstein called this spooky action at a distance, and he wasn't being complimentary. He thought it meant quantum mechanics was incomplete. But every experiment since then has sided with quantum mechanics. Entanglement is real. So you create an entangled pair. You send one particle to Alice and the other to Bob. They could be across a room or across a continent. Doesn't matter. Alice has a third particle, the particle whose quantum state she wants to teleport. She does not know what state it's in. She cannot look at it to find out, because looking at it would change it. That's the whole problem. She needs to get this state to Bob without learning what it is. She takes her teleportation particle and her half of the entangled pair and performs a very specific joint measurement on them, not a measurement on each one separately.